All right, hi all, this is Mr. Yeager. We are going to look at basically the idea of forces when we're pushing multiple objects. This is a very, very common problem in AP Physics, and it's one that they will usually leave the answer in terms of symbols, no numbers really necessarily involved. So we have to understand what is occurring here. What does the one object feel versus the other? What's similar between the two objects themselves, okay? And so we're going to start off with this problem that you see here. Basically, we have a force pushing on box M, but M is directly next to 3M. And so basically this force is having to push both this box M and this box 3M. And so what we are primarily going to look at here is what is the acceleration on each object. These are the two most common questions on this. What are the two most common, what is the acceleration on each object? And then what is the net force on each object? And we're going to look at this, you're going to have to be able to do this on a frictionless surface and a surface with friction. They could give you either one of those types of problems, okay? So that is what we are going to focus on for this particular section. All right, so the first thing is, what we need to know is when you push on these objects and they are in contact with each other, the objects move together. The object's movement is together, okay? So what would be the same about both of them? Okay, the same would be, each one would have the same acceleration. It's impossible to say that 3M is accelerating faster than M, or vice versa. I can see a lot of people think box M is accelerating faster because it's smaller. All right, but the thing is, these two objects are directly against each other. When I start pushing M, 3M is going to move right along with it as fast and will accelerate with it just as quickly as little m, okay, the 1m. So the acceleration on both boxes is the same. And so this basic problem, we're going to use the idea of the system approach again. In other words, look at this as a group. Look at this as one object that has a mass of 4m being pushed by a force F. All right, 4m being pushed by a force F. All right, it's going to be the exact same acceleration as a force pushing m, which is then pushed against 3m. All right, so we're going to use the system approach to try to solve for acceleration and then go back and solve for the net force on both boxes. All right, so we need to first figure out the acceleration. So once you have the acceleration, look at each object individually to find the force on each object. So let's figure out the acceleration. All right, so if I make it a system approach, that would mean that I'm pushing this object with a force F. There's no friction, so I mean, if I want to be more official, my free body diagram would look like this: F, normal, and weight. I am on a flat surface and no friction. The thing is, this object is moving to the right, so the normal and the weight, they're not going to be involved with the net force. They're going to simply be equal to each other. So what I can say here is F net equals m times a equals sum of forces. This is the formula I'm going to use. So F net equals, what's my mass? 4m times a equals what forces are making this accelerate. The only force that's going to make it accelerate is F. So 4ma equals F. So that means the acceleration is equal to F over 4m. That would be your answer. Again, by now you're pretty much used to the idea that we almost never use numbers and everything comes out in just symbol form. Okay? So A equals F over 4m. All right? So once I have that, once I know that, sorry, I want to see something. Okay? Yep. Once I have that, right, so now I know that the acceleration on both boxes is F over 4m. Both boxes are accelerating together with an acceleration of F over 4m. I can now find the net force acting on each box. Sorry, let's erase all that. Okay. So let's look at the net force on M. Net force on M would be m times the acceleration, F over 4m. So what net force does the first box feel? It would be F over 4. I cancel out the m's. That would be the net force on M, What about the net force on 3M? The net force on 3M, okay? The net force on 3M would be 3M A time equals, what am I doing here? No, I'm being silly here, sorry. I already know what A is. Why am I just saying A? 3M times F over 4M. Once again, M cancels out, so this will be 3F over 4. I'm sure some of you guys obviously see, basically, it comes out to a ratio, all right? If you have these two boxes, each one will feel that appropriate percentage of the net force that this object obviously does feel overall based on their masses. I mean, that's basically fine to do as well, okay? So those would be the net force. So one of the big things to notice here is while the acceleration is the same for both boxes, the net force is not the same because they have different masses, all right? So the net force is not the same because of different masses, all right? Because of different masses. Now, I'm going to add one more thing to this. Because sometimes this gets confusing for people. All right? I'm going to erase all this. All right? In some problems, they will talk about, they want you to find the pushing force of M on 3M. They call that a force P. This is often in some web assigns that I give. What is the pushing force between M and 3M? So this kind of goes to that third law idea. If we had to draw a specific free body diagram just for M, and we say P is the force that M pushes on 3M, we would say that M is being pushed with a force F. This force F is a contact force. It is only directly in contact with M. M is the only one that actually feels the force of F. Obviously, some of that force is then transferred by a force created by M on 3M. So M is being pushed by F, but technically pushed back by P. All right, P is the pushing force. Again, Newton's third law. M pushes on 3M with a force P. 3M pushes on M with a force P. All right, it doesn't matter what the motion is. The direct force between two objects must be the same. All right, equal opposite forces, Newton's third law. What does 3M feel? 3M would technically only feel force P. Again, there's no friction involved. All right, and so if they said, what was force P? Well, that's the net force on 3M, which we just found. Net force is equal to P, which is equal to 3M times F over 4M. So P equals 3F over 4M, which then makes sense for M, because I can say net force equals F minus P, and I said F minus 3F over, sorry, get rid of this M. All right, sorry. So P is 3F over 4. F minus P, F minus 3F over 4 leaves me with just F over 4 as the net force on box M. Okay? So be aware of that. If you need to go back through that one more time to kind of really get the idea, do it. Okay? So that's a very common situation that they might throw at you. Now, what if we add friction to it? Okay? What if it's not friction? You are given mu. Find the acceleration. All right? So we basically do the exact same thing again. I'm not going to do the second part, but you can hopefully try to put the second part together again. This is 4M now being pushed with a force F, but there's a force of friction going back in the opposite direction. Again, technically, there's also weight and normal. Okay? So what would we do here? This would be F net equals 4M times A equals F minus force of friction. Now, if the problem says, I mean, this is where you got to read it. They do these problems all different ways. There are problems where they'll just say, assume friction is F. You could just then leave it as F. Okay, you could just leave it as lowercase f in the problem. But what if the problem is saying, I want the acceleration in terms of mf mu, and any physical constants. And I can't spell. I'm going to abbreviate. Physical constants. All right? That means I can't leave it as f of f. F of f is not one of my choices. I can keep f, but not f of f. So what do I need to do here? It'd be 4ma equals f minus, and we have gone over this enough now. What does ff equal? Ff is mu normal, which is equal to mu weight, because they're equal to each other. You're on a flat surface, which is mu mg. So now this would be mu mg. Okay? Then I divide the 4m on both sides, and you would be left with, sorry for acceleration. You would be left with a equals f over 4m, they like to usually reduce the sum, minus mu g, because the mu g over 4. Okay, mu g over 4. You'd obviously get rid of the m's on both of them. It's possible that they could leave the whole thing. It could be just f minus mu mg over 4m. I mean, that's a possible answer as well. But basically the idea is we have obviously a more complicated answer to it. Okay? What would be the net force? Then obviously we go even farther with it. So it gets obviously more and more complicated as we move forward with it. Okay? So that is what we would do if it has friction on it. All right? I would just add in that mu mg and solve for it the exact same way. Both objects would feel this acceleration, and then basically I'd multiply this acceleration by m to find the net force for m, 3m to find the net force for 3m. All right, next situation. What if we have two objects that are accelerating up or down? What happens to the tension? All right, so this is very much like the elevator problems. Again, these objects will accelerate together. The top tension will always be greater than the lower tension because the top tension is holding the total mass. Okay, it's holding all of the masses. The bottom tension is holding the lower mass. But this is exactly like the elevator problems that I hope that you have already worked on some. And the only difference is we're going to add T in instead of using the normal force. Obviously, if you're pulling up, tension will be greater. If it's falling, tension will be less than the weight. Okay? So if I find the tension, we're just doing a quick problem here. Find the tensions in both ropes if you accelerate upward at 5 meters per second squared. All right? So the way I would look at this is instead of looking at two objects, I would make it a system. It's a 4 kilogram object being held up by T1 and then the total weight. And then I would do F net equals MA equals T minus T1 minus the weight. And then I could find T1 will equal MA plus the weight. So T1 will be MA plus MG. And I'm going to go ahead and keep reducing this, MA plus G. And so this would be 4 times 5 plus 10. So the top tension would be 60 newtons. Okay? The top tension would be 60 newtons. All right? What would be the bottom tension? What would be the bottom tension? Okay? You're finding that that was the top tension. The bottom tension would just be basically the same thing. F net equals T minus the weight, T2 minus the weight. The bottom tension is only holding up the 3 kilogram mass. And so I'm going to really speed this one up, speed it up. This would be 3 times 5 plus 10. So this would be 45 newtons on the bottom. Okay, 45 newtons. So top one would feel 60 newtons, bottom would be 45 newtons. Okay, and that's it. All right, and again, that's greater than the weight. Both of them are greater than the weight because they're accelerating upwards. All right. What if you accelerate downwards at 2 meters per second squared? All right, I'm going to go pretty quick with these. You'd go F net equals MA equals, this one would be weight minus tension. Okay? Again and again and again. Okay? It doesn't tell you which way you're going, so I'm going to assume down is the way that this is moving and it's accelerating downwards. Okay? I'm making an assumption there. If you say up is positive, you're going to have to obviously be careful with your numbers. You're going to have a negative A. Okay? But again, with system problems, All right, if they don't give you the direction, just make the direction of the acceleration, just to keep the acceleration positive. Okay, so if I do this problem, it would be T1 over the weight. Okay, T1 going up, weight going down. And if I solve this one, rearrange it, it would be T equals weight minus MA. And so this would be mg minus A. That's good because, again, my tension should be less than the weight. And so the T1 up top, I'd call this T1, this T2. T1 would be, total mass 10 times 10 minus 2 equals 80 newtons. Good, because the total weight is 100 newtons, so the tension is less. T2, this would be T2 equals 9 times 10 minus 2. That would be 72 newtons. Okay? So that's how you handle both of those. Last examples that I have here is, what about tension if you're pulling two objects horizontally? Exact same thing as the initial problem. Exact same thing. Okay? The acceleration will be the same on both objects. The only big thing is that the tension between the objects will remain the same regardless of the friction involved. All right? Check. All right, so as I was saying, if you have these two objects being pulled together, even with the rope, the acceleration on both objects will remain the same. Now, one unique thing that will happen is the tension between the objects will actually remain the same as long as you keep pulling with the exact same amount of force, no matter what the friction ends up being. The tension between the objects will actually remain the same. All right? So I think we have a problem. Okay? So find the acceleration and tension between the objects when it's frictionless and when you have a mu of 0.1. All right? So again, I'm going to run through it fairly quickly. Basically, you make it into a system again. So you have a 10 kilogram object being pulled by a force of 200 newtons. Okay, I'm doing part A, so there's no friction. So basically, I can immediately solve for the acceleration. All right, it would be F net equals ma. This would be 100. Again, that would be the 100. What am I doing? Sorry. That would be 10 times a equals 200. So the acceleration on this object would be 20 meters per second squared. That would then mean, what's the tension in the second rope? What would be the tension in the second rope? Well, the 2 kilogram object is only being pulled by that rope in between. There's no friction, so that therefore I already know what's accelerating, so net force would equal the tension, which would equal 2 times 20. So it would be 40 newtons. Okay, it would be 40 newtons. All right, so that's the first one. Now the thing is, you're going to see in a minute that actually this will remain 40 newtons for the second one as well. The tension actually remains the same as long as the force being applied remains the same. So if I try again, okay, but now with friction. Okay, so we said this is going to come out to 40 newtons. Watch this. What if we have now a coefficient of friction of 0.1? Well, now I have that 10 kilogram object again, still being pulled by 200 newtons, but now there's a force of friction. Now there's a force of friction involved. All right. What would that force of friction be? That would equal mu mg, which would be 100 times 0.1. 0.1 times 100 is 10 newtons. So we got 10 newtons going back. So now this would mean that we basically have a net force of 190. Once again, equals 10 times A, so A would equal 19 meters per second squared. So it gets slowed down a little bit. That's not much friction. 0.1 is almost like ice. All right. So only a slightly smaller acceleration. So let's figure out what happens down here. Some people might go, wait a minute, no, it's not going to come out the same. 2 times 19 is 38. You're forgetting something. This 2 kilogram block now feels friction. So we have tension to the right, but a frictional force back to the left. So now this would be F net equals 2 times 19. That is correct. It still accelerates at 19 meters per second squared. It'll equal T minus the frictional force. Well, the frictional force for this would be 0.1 times 2 times 10. How much is that? That's 2. So what do we get here? I get 38 equals T minus 2. What? I'm going to add 2? The tension comes out to 40. Crazy. All right. So again, I want to make that clear. I think some people sometimes get confused. They go, oh, the tension between there stays the same no matter what. It stays the same as long as that pulling force stays the same. You can do whatever you want to the frictional, the coefficient of friction. As long as that pulling force is the same, it will actually always still come out to the same total amount on the tension between those two blocks. All right, so that is it. That is it. That is it. Okay. Thank you.